Welcome to this quick tip video where we'll be discussing the mesh technology available in Simcenter FLOEFD. For our first example, we'll be looking at a 2D airfoil section called the RAE 2822, which is a very common wing profile used for benchmarking CFD simulation software. We can see the actual wing geometry here, and also a transparent enveloping body, the computational domain. We can see that this is an external flow analysis which is being solved in 2D. The size of the computational domain is user-defined here and the 2D option already selected. Let's now have a look at the base mesh settings. The default mesh settings in Simcenter FLOEFD are controlled by an automatic mesher. We can overlay the base mesh onto the screen and move the slider bar to preview the mesh at different levels. As we can see, Simcenter FLOEFD uses a Cartesian mesh to solve the finite volume Navier-Stokes equations. We can disable the uniform mesh option, which then stretches the mesh to achieve a coarser grid in the far field away from the action. We have the option of disabling the automatic mesh settings and using a manually defined mesh. This gives the user access to the number of cells in the X, Y, and Z directions, the control planes, and also to the cells ratio definition. In addition to the base mesh settings, we can use the local mesh option to manually apply additional grid in areas or volumes of interest. We can select the surfaces of this airfoil and define a refinement level for the cells at the boundary between solid and fluid. We can use these surfaces also to apply an equidistant refinement. In this example, we define two shells. These shells are counted out from the selected surfaces, and the initial mesh cells will be split with the same refinement level in each of them. Finally, we define the offset distances for the two shells, 200 mm for the first and 400 mm for the second offset. Let's now have a look at the mesh created. The first is the default mesh using the base settings, plus our local initial mesh, and has approximately 46,000 cells. The mesh system in Simcenter FLOEFD works using levels, which are shown here colored from blue to red. The base mesh is referred to as level 0 octree. Mesh refining means that a single cell is then split into 8 cells to go to the next level up. We can see level 0 to 3 grid cells in the fluid region and level 4 at the walls at this stage. The equidistant local initial mesh region can clearly be seen around the wing section. In the far field, we have very large grid cells away from the lifting surface, and closer in they get smaller in the user-defined region. On the actual surface of the wing, we can see even smaller cells. Another aspect of the meshing technology in Simcenter FLOEFD is the solution adaptive meshing capability. This allows for automatic refinement of the mesh in high flow gradient areas in the solution. Again, based on the level system, we can restrict the software on how small the grid cells can be. The mesh density will increase only in areas which are required, which makes for a very efficient mesh. We can now see a spread of refined grid cells created by the solution adaptive mesh refinement based on flow gradients. The mesh refinement also occurs in the wake zone behind the wing to capture these flow gradients in higher resolution. The final mesh, after several adaptive refinements, has over 300,000 grid cells. Additionally refined grid cells can now be seen at the leading and trailing edges, as well as the shockwave location. Finally, showing a cut plot of Mach number shows a nice crisp shockwave as a result of our high mesh count. In the second example, we'll be looking at a mixing application with two gases. Here we can see a section of ductwork equipped with a louver damper and an injector pipe with a hot gas inflow. The animation shows the inlet flow profile of the hot gas through the small pipe, then an initial mixture caused by the depth of the pipe position into the main flow. Afterwards, a greater mixing of hot and cold gas generated by the vortices in the flap is visible. Similar to the first example, we define a global basic mesh, here defined by manual settings with an initial number of cells in the X, Y, and Z direction. In addition, the solution adaptive refinement is activated for refinement in areas with high gradients, in this application high temperature differences, for example in the mixing regions. This plot shows the initial mesh with the geometrical refinement only, for example at the blades in the valve and the hot gas inlet pipe. Now we can see the first and second solution adaptive refinement, which is based on the gradients, for example in regions with high temperature gradients and recirculation areas. Different cut plots show several regions of the results and the refinement. The visualized parameter is temperature. The hot gas is shown red, and we can clearly see the mixing behavior in the larger duct, behind the protruding small pipe and in the damper area. These plots can also be dynamically moved directly in the CAD model, and we can see the refinement in and around the high temperature core flow. Being completely CAD embedded, Simcenter FLOEFD allows us this intuitive and efficient post-processing, as well as the powerful meshing technology based on flow effects and on the real CAD geometry at the same time.